Newton's first law of motion states that an object at rest tends to stay at rest, and an object in motion tends to stay in motion at the same speed and in the same direction unless acted upon by an unbalanced force. This law is also known as the law of inertia. Inertia is the resistance of any physical object to a change in its state of motion or rest, or the tendency of an object to resist any change in its motion. This means that there is a natural tendency of objects to keep on doing what they are doing. All objects resist changes in their state of motion. In the absence of an unbalanced force, an object in motion will maintain its state of motion.
Unbalanced forces are the forces that make objects speed up, slow down, or change direction. In the first example, a force is being applied to the car, causing it to speed up. In the second example, a force is being applied in the negative direction, causing it to slow down. And in the third example, the centripetal force on the ball is causing it to change direction.
When we use a hard-boiled egg and I apply the force of my hand to it, the entire egg system will stop since the inside of the egg is no longer liquid and spinning independently of the shell. It is now one solid system.
We will now use the game of pool to summarize Newton's three laws of motion. For the first law, an object at rest will remain at rest unless it is acted on by an external force. We have the cue ball at rest on the table. It will remain that way until an external force, like the cue, exerts a force on it. This will cause the cue ball to change its state of motion.
Newton's second law of motion states that the acceleration of an object as produced by a net force is directly proportional to the magnitude of the net force in the same direction as the net force and inversely proportional to the mass of the object. The equation that governs this law is F equals ma, the force equals mass times acceleration.
Here's an application of Newton's second law of motion. A mass m1, which weighs 6.2 kilograms, rests on a frictionless table. It is connected by a massless and frictionless pulley to a second mass, m2, which equals 3 kilograms, which hangs freely. Here we are solving for the magnitude of acceleration of block 1. The equation is set up as acceleration equals force, which equals m2 times gravity, divided by the total mass of the system. When we plug in the numbers and work out the equation, we find that the acceleration of block 1 equals 3.19 meters per second squared.
Here is an example of Newton's second law of motion. We found that the weight of this eraser is 9.8 grams. When we put the scale in an elevator, the weight of the eraser changes because the acceleration due to gravity causes the force pushing the eraser down to change.
For Newton's second law, we have the cue ball being hit into the one ball. If we assume that it is an elastic collision, the acceleration of the one ball is directly proportional to the amount of force imparted on it from the one ball.
A good example of Newton's second law is basketball. When you shoot a basketball, it weighs 0.62 kilograms. This means that it takes a force of 5.2 newtons to shoot a 3.
If you were to shoot a medicine ball, however, that weighs 2 kilograms, it would take a force of 16.8 newtons to shoot a 3.
Newton's third law of motion states that for every action there is an equal and opposite reaction. Here is an example of Newton's third law. When a person pushes off the wall pushes back on the person. Here we can clearly see that when the person pushed off the wall pushed back on the person, causing him to accelerate in the opposite direction.